So let's talk about a concept that sounds super intimidating, but is actually the key to understanding, well, pretty much everything that changes around us. It's called the derivative. From the speed of your car to how a company grows, this is the tool that lets us see change not over a year or an hour, but in a single instant. Okay, so picture this. Measuring the steepness, the slope of a straight hill, that's easy. But what about a roller coaster? The track is curving and changing at every single moment. How in the world do you find the exact steepness right at the very peak or in the middle of that heart-pounding drop?
All right, so how do we crack this puzzle? It all comes down to finding a completely new way of thinking about the slope when you're dealing with a curve. I mean, a straight line is a piece of cake, right? It has the same slope everywhere. But a curve is a totally different beast. Its steepness is constantly in flux, so you can't just use one number to describe the whole thing. It just doesn't work. This is where the truly brilliant idea comes into play. Instead of trying to look at the whole curve all at once, what if we just zoomed in? And I mean really zoomed in, focusing on one impossibly tiny, almost microscopic piece of it. And here's the magic. As you get closer and closer, that little piece of the curve starts to look almost perfectly straight. For any smooth curve, if you zoom in far enough, it becomes practically indistinguishable from a tiny straight line segment. And that tiny straight line we've zoomed in on? Well, it's part of a bigger line, something we call the tangent line. It's the one line that just kisses the curve at that single specific point. And here's the kicker. The slope of that tangent line is the slope of the curve at that exact instantaneous moment. That's the number we've been searching for.
Okay, so this whole powerful process of finding the slope of the tangent line at any point, well, it's got a name, and it's the core concept for this entire explainer. We call it the derivative. And the derivative isn't just a number, it's a whole new function that you can create from your original function. Its entire job, its purpose in life, is to tell you the slope, that instantaneous rate of change, for every single point on the original curve. It's like a universal slope-finding machine. Now, of course, mathematicians love having different ways to write things. Gottfried Leibniz gave us this dy over dx notation. You can just think of it as a tiny little change in y over a tiny little change in x. Then, Joseph Louis Lagrange gave us the super simple f prime of x, which we just say as f prime of x. They look totally different, but don't let that fool you. They mean the exact same thing, the derivative.
Now, this is where it all clicks. Seriously, the best way to truly get a feel for the derivative is to see the relationship between a function's graph and the graph of its derivative, side by side.
So, we're going to look at two graphs. On the left, we'll have our original function, let's call it f of x, and on the right, we're going to have its derivative, f prime of x. What I want you to do is pay super close attention to the connection between them.
Let's start simple. The function on the left is just a straight line with a slope of 1. It's going up at a constant rate. So since the slope is always 1, the derivative graph on the right is just a flat, horizontal line at a height of 1. A constant slope means a constant height for the derivative. Makes sense, right?
Okay, now for a curve, a classic parabola. Look at the function on the left. As we come in from the left side, the slope is steep and negative. It's going downhill fast. Then, right at the very bottom, the curve flattens out for just an instant, and the slope is exactly 0. Then, as we move up the right side, the slope becomes positive and gets steeper and steeper.
And here is the beautiful connection. The derivative function on the right captures the story perfectly. The height of the derivative graph mirrors the slope of the original graph. When the slope was negative, the derivative's graph is below the axis. Its value is negative. When the slope hits 0, the derivative's graph crosses the axis. Its value is 0. And when the slope turned positive, the derivative's graph is above the axis. It's a perfect match.
This is it. This is the single most important idea to take away from all of this. Let me say it again because it's that important. The slope of the original function at any point you pick is equal to the height of the derivative's graph at that very same point. They're two sides of the same coin.
So why is this such a big deal? Well, because this relationship is like a superpower. It means we can understand how a function is behaving, whether it's increasing or decreasing, just by looking at its derivative.
And the rules are super straightforward. If the derivative graph is positive, meaning it's literally above the x-axis, that tells us the original function slope is positive. So the original function must be increasing. It's going uphill. If the derivative is negative, below the axis, then the original function is decreasing. It's going downhill. It's that simple.
All right, time for a little pop quiz. Here is the graph of a derivative. Now, I'm not showing you the original function at all. Just by looking at this graph, can you tell me where the original function, f of x, is increasing?
The original function is going to be increasing wherever its derivative is positive. And where is this graph positive? Well, it's above the x-axis for all the x values between -2 and +2. So in that whole stretch, we know for a fact the original function is climbing uphill.
Okay, now for a curveball. What about a function with a sharp corner, like an absolute value graph that looks like a V? As you come towards the point from the left, the slope is one thing, say -1. As you leave to the right, it's suddenly something totally different, like +1. So what in the world is the slope exactly at that sharp corner?
The answer is, there isn't one. At a sharp corner, you can't draw one single clear tangent line. You could wobble it back and forth. Because of this, we just say the derivative is undefined at that point. Our slope-finding machine basically throws up its hands and says, sorry, I don't have an answer for you right there.
All right, let's zoom all the way out. We've seen what a derivative is and how it works, but why is this one idea so important that it basically helped launch a scientific revolution?
Because the derivative is, quite literally, the language of change. If you want to find the absolute highest point of a profit curve, or the lowest point in a valley, you just find where its derivative, its slope, is 0. In physics, it's everything. The derivative of your position is your velocity, and the derivative of your velocity is your acceleration. It is the engine behind models for population growth, the stock market, you name it. If something in the universe is changing, derivatives are how we describe it.
So we'll end on this thought. We've just explored the mathematical tool for understanding change as it happens in a single instant. So the question I want to leave you with is this. What changing system, what rate of change, what dynamic process out there in the world do you think is the most critical for us to analyze and understand right now?